In the skies above us, every second counts. From takeoff to touchdown, pilots manage a complex ballet of altitude, speed, trajectory, and safety guided not just by skill but by sophisticated systems working quietly in the background. Welcome to the world of flight path management systems, the digital brain that charts a course through crowded airspace, changing weather, and thousands of real time variables. In this video, we'll uncover how flight path management systems powered by the Flight Management and Guidance Computers or the FMGC have transformed modern aviation from reducing pilot workload to enabling long-haul flights across oceans and continents. These systems are the unsung heroes of global air travel.
Hello, my name is Preetam Kadam from University of Würzburg.
Hello, I'm Chaitanya Athavle from University of Würzburg.
Welcome to this presentation on flight path management in modern aircraft. Today we will explore how aircraft maintain precise trajectories from takeoff to landing using advanced avionics, control systems and navigation tools.
Whether you're flying on a commercial jet, piloting a business jet, or monitoring an autonomous drone, flight path management plays a central role in ensuring safety, efficiency, and regulatory compliance. It's one of the most crucial technologies in aviation today.
We'll break down how these systems work, look at their components, challenges and even future trends. Let's get started.
What is flight path management?
Flight Path Management or FPM refers to the integration of trajectory planning, guidance, and control systems. In essence, it's what makes sure an aircraft travels safely and accurately along a pre planned route. Think of it like a highly intelligent GPS system combined with real time decision making and autopilot capabilities, but scaled up for complex 3D navigation and dynamic airspace conditions.
FPM systems calculate the ideal path for an aircraft based on factors like waypoints, weather conditions, airspace restrictions, terrain, and also performance data. These paths are constantly refined and adjusted mid flight. Modern FPM doesn't just get you from point A to point B, it ensures compliance with flight regulations, noise abatement procedures, fuel economy, and precise timing requirements in congested airspaces. Core components of FPM.
Let's break down the main building blocks of a flight path management system.
First, at the heart of it all is the Flight Management System or FMS. The FMS is essentially the brain behind the mission. Pilots input their desired route, including waypoints, speed constraints, and altitude restrictions, and the FMS calculates the best path in both lateral and vertical dimensions.
It factors in fuel predictions, aircraft weight, winds aloft, and even anticipated holding patterns. As the flight progresses, the FMS constantly compares real time data against its planned trajectory and makes minor course corrections.
Next, we have the autopilot and flight director systems. These are the muscle of the operation. The autopilot executes the command computed by the FMS, manipulating the aircraft's control surfaces to follow the programmed route. The flight director provides visual cues to the pilot, indicating what manual corrections would be needed if autopilot weren't active.
Then there are the navigation systems, such as GPS, inertial navigation system, that's INS, and ground based aids like VOR and DME. These tools work in combination to track the aircraft's position precisely, often with multiple layers of redundancy.
We also have the air data systems, which monitors environmental conditions like airspeed, pressure, and temperature. These variables are crucial for adjusting aircraft performance and flight profiles in real time.
All these systems must work together flawlessly. If even one input is compromised, the aircraft's path could drift, making coordination and backup systems essential. Path guidance and flight phases.
Now, how do these systems guide an aircraft throughout its journey?
Flight path management operates in both the lateral and vertical planes. Lateral navigation or LNAV governs the horizontal path, the left to right movement that follows a series of programmed waypoints. Vertical navigation or VNAV controls the altitude profile from climb to cruise to descent.
Modern FPM systems divide a flight into distinct phases: takeoff, cruise, descent, approach, and landing. Each phase requires its own logic, constraints, and safety buffers.
For example, during takeoff, FPM system ensures adherence to noise abatement procedures and early altitude constraints. In climb, VNAV ensures the aircraft doesn't exceed structural speed limits or the climb rates.
At cruise, the system switches to fuel efficiency mode, optimizing for tailwinds and ideal altitudes. As the aircraft descends, the FPM predicts top of descent points and calculates the most efficient glide path towards the runway.
Many modern aircraft now use 4D trajectory management. This includes not just latitude, longitude, and altitude, but also time, ensuring the aircraft arrives at critical waypoints with pinpoint temporal accuracy.
This is especially crucial in congested terminal areas where spacing and sequencing are tightly coordinated to avoid traffic congestions and reduce holding. Integration with avionics and automation.
In today's glass cockpit aircraft, flight path management is integrated deeply with modern avionics systems. Pilots interact with the FMS via multifunction displays and control display unit (CDUs), often using touchscreens or rotary knobs.
The flight path logic flows from the pilot's input into the FMS, which sends instructions to the autopilot and flight control computers. These then translate the digital commands into mechanical actuation via hydraulic or electrical control systems.
This type of closed loop control system means pilots monitor rather than actively control the aircraft most of the time. However, they remain engaged, especially during climb, descent, and unexpected deviations.
An excellent example of this integration is an RNAV approach, a type of arrival procedure where the aircraft uses satellite navigation instead of ground based radio aids. These approaches can guide aircraft precisely from down to the runway threshold, even in low visibility.
Such automation not only reduces pilot workload but also allows more aircraft to operate in limited airspace, thereby improving efficiency. Challenges in flight path management.
As advanced as these systems are, they are not without challenges.
One major issue is data integrity. GPS outages, INS drift, or environmental anomalies can cause the aircraft to deviate. Most systems are designed with multiple fail safes, but occasional anomalies can still occur, particularly in remote regions or during solar disturbances.
Then there's the problem of weather unpredictability. Severe turbulences, wind shear, or sudden icing conditions can all force deviations from a planned flight. The FPM must react quickly to re-optimize the routes while keeping within safety margins. While keeping within safety margins.
Another critical aspect is human machine interaction. Despite automation, pilots must understand what the system is doing and why. In some incidents, misunderstanding about FMS behavior have led to confusion or inappropriate responses, especially during approach or missed approach phases.
Lastly, with increasing connectivity in avionics, cybersecurity has become a growing concern. Unprotected data links or unsecured firmware can potentially open the door to intrusions, a risk the aviation industry is now taking very seriously.
Future trends.
Flight path management is on the verge of new evolution, with several emerging technologies poised to redefine how we think about aircraft trajectories.
One such concept is trajectory based operations or TBO. Under programs like NextGen in the US and CESAR in Europe, aircraft will communicate their intended paths in real time with air traffic control and dynamically reoptimize those paths based on current traffic and weather.
Another trend is the integration of artificial intelligence and machine learning in the FMS. These systems will be able to predict weather patterns, passenger demand, and congestions and adapt routing autonomously.
This will be especially important for unmanned aerial vehicles or UAVs and urban air mobility UAM platforms, where thousands of autonomous aircraft might be sharing airspace over cities, each requiring constant coordination.
One of the most exciting developments is the use of digital twins. Real time virtual replicas of aircraft systems that can simulate scenarios, flight paths, and predict outcomes before they happen. These will be not just used for flight planning but also for maintenance and safety. Welcome to the Flight Simulator Lab at the University of Würzburg. Here we'll take you on a short tour inside our Airbus A320 base simulator. This immersive setup helps us explore the flight path management system in action, including key components like the flight management and guidance computer, the flight control unit, and the primary flight display. We'll also show you how these systems are positioned in the cockpit and give you a brief idea of how they are used during flight.
In this section, we'll walk through programming the Flight Management and Guidance Computer or FMGC for a short domestic flight from Ibiza Airport LEIB LIB to Palma de Mallorca Airport LEPA LEPA using the Airbus A320 simulator. We begin by powering up the system and heading to the MCDU Multifunctional Control and Display Unit. On the Init A page, we enter our departure airport LIB and arrival airport LEPA. The route is automatically loaded into the FMGC's memory. Once the route is defined, we go back to the Init B page to input our cruise altitude, 24,000 feet, and estimated cost index. We then proceed to the performance page to enter takeoff performance data, including flap settings, transition altitude, and expected wind component. The flex temperature setting is also added here. Next, we proceed to the flight plan page. From here, we input the departure runway, runway 06, and select the associated standard instrument departure or SID. In this case, we choose the appropriate SID based on expected traffic and weather conditions. With the departure set, we begin inserting en route waypoints. These points define the lateral navigation the aircraft will follow. Each waypoint is typed into the MCDU and confirmed with the insert key. After setting the route, we move on to the arrival into LEPA. We select the standard terminal arrival route corresponding to runway 24R, which is the active runway in Palma today. This includes the transition and approach procedure which the FMGC will use to guide descent and alignment with the runway. The MCDU now contains a complete 4D trajectory from takeoff to landing, incorporating both lateral and vertical guidance. Then we enter the performance section where we input the critical takeoff velocity V1, VR, and V2, and also flex temp and flaps setting. Before takeoff, we review the route on the navigation display to confirm all waypoints, altitude constraints, and speed limits if they are correctly set or not. Once airborne, the FMGC will manage the aircraft's path according to this data, reducing pilot workload and ensuring an efficient and safe flight. This hands-on training allows us students to fully understand the interaction between systems like the FMGC, the FCU, and the autopilot, building confidence in both manual and automated flight management.
This is the Flight Control Unit, or FCU, an essential part of Airbus A320's flight deck. It allows pilots to interact directly with the autopilot, auto thrust, and flight director systems. Using the knob push-pull controls, we can manage speed, heading, altitude, and vertical speed. The FCU displays selected values digitally, offering clear feedback to the crew. Push commands let the FMGC guide the aircraft automatically, while pull commands allow manual control inputs. This design supports Airbus's flight philosophy, managed automation with pilot authority. In simulator training, the FCU helps students practice transitioning between manual and automatic flight modes with confidence.
The primary flight display or PFD provides critical flight information, altitude, airspeed, vertical speed, and flight director guidance all in one place. It's designed to give the pilot instant situational awareness during all phases of flight. Next to it is the navigation display or ND, which shows the aircraft's lateral flight path, waypoints, nav aids, and weather radar. It also displays the heading and track, helping pilots monitor route progress and detect any deviations. Together, the PFD and ND form the core of the Airbus cockpit's glass instrumentation, supporting both manual flying and automated guidance as we talked about it in earlier slides.
The ECAM, or Electronic Centralized Aircraft Monitoring System, is one of the key display systems in the Airbus A320. It consists of two screens. The upper display shows engine parameters and key flight information, while the lower display provides system status, configuration changes, and alert messages. ECAM continuously monitors all major aircraft systems, including hydraulics, fuel, electrical, and pressurization. In case of a failure or warning, ECAM automatically displays the relevant page and guides the crew through the proper checklist. This smart integrated design reduces pilot workload and enhances safety, making it a powerful tool for both training and real world operations. Flight path management is the silent intelligence that allows modern aircraft to navigate vast, complex skies with accuracy and safety.
It combines deep system integration, real time data analysis, automation, and human oversight to create a resilient and flexible navigational framework.
As we move towards more autonomous flight and increasingly crowded skies, Flight path management will become more predictive, adaptive, and intelligent.
Whether you are in the cockpit or on the ground, understanding how these systems work is vital to appreciating the sophistication of modern aviation.
Thank you for joining us. We hope the presentation has helped you understand not only how flight path management works, but why it's so essential in the future of flight.
And also don't forget to answer the quiz question